another website. This one is in St. Andrews in the UK that has a nice graphic to illustrate how these wave functions are represented in 3 dimensions. Okay, so let me show you that website. All right, so when you get to this website, click on the step-by-step exploration. Look at slides 2 and 3. This particular website deals with the hydrogen wave functions in particular, and part of that wave function would be a spherical harmonic. So slide number 2 right here is a representation of the spherical harmonic for L equals 0, M equals 0. Okay. And if you remember, this particular spherical harmonic, the value of psi is just a constant, right? So psi in this case, which is y, 0, 0, is just a constant. And so if you plot that in spherical polar coordinates, what you do is for any particular direction, okay, theta and phi, the distance from the origin to the point is just the value of the square of the absolute value of psi. So since psi is constant, then what do you call all the points that are equidistant from a given point? A circle if you're dealing with a plane, but if you're thinking 3 dimensions, that's a sphere. So the spherical harmonic for L equals 0, M equals 0 is represented by a sphere. Okay? And that is in fact part of the wave function for what you've learned as the s orbital of hydrogen. Okay? Part that depends on theta and phi. So here's another, slide 3 on this website. Here's another representation of I believe this is for L equals 1, M equals plus or minus 1. Okay, where you'll notice you have a node at the z-axis. Okay, so this thing looks like a donut. So again, the distance at any given point. So for a specified theta and phi, the distance of that point from the origin is directly proportional to the square of the value of the wave function at that point. Okay, so you can see how that changes by angle. So if you try different angles, okay, so you can if you're changing your theta, what is theta? That's the angle from the z-axis, right? So you can see here that as your theta approaches pi over 2 in this particular case, what happens? The point gets further and farther away. So as it approaches 90 degrees, the point gets further and farther away from the origin, right? So this point right here is at this theta. This is a bigger theta. It's farther away from the origin, and so you can say then that in that particular direction, at that particular location, there's a higher probability of finding the point. So if L equals 1, M equals plus or minus 1, there's a high probability of finding your particle, you could say, at the equator of your sphere, at theta equals pi over 2, at the xy plane. There's 0 probability of finding it at the North Pole of your sphere. Okay? So that's a visual representation of L equals 1, M equals plus or minus 1. And this website from France gives you an animation that where there's a color-coded mapping of the value of psi as time changes. So this gives you the complete time dependent. So this is not just dependent. I'm sorry. This is not just dependent on theta and phi. This is actually psi as a function of theta, phi, and time. So it shows you the oscillation in the wave function itself at a particular location with time. Okay. But since we're dealing with stationary states, psi squared is going to be constant, right? It's going to be independent of time. but it will vary. The function itself will be varying with time. We've seen that several times before already. That has the animated representations of your wave function. So you can see the color mapping there tells you the value of psi. Okay, so when it turns red, it's more positive. If it turns blue, it's more negative. Okay, and it's at every point on the sphere, it's oscillating with time. Okay, but if you were to plot the square of the wave function, the square of the magnitude of the wave function, then it's going to be a stationary state. You're not going to see that changing. This is the function itself being changing with time.